All right, so let's talk through number 23 and 2.2. So, this problem is that I'm supposed to solve this IVP and then find the interval of validity. Okay, so first things first, Jacob, how did you go about trying to solve this? What did you do?
I subtracted the y to the other side, divided the two x terms, and then divided the y back to the other side.
Okay, so we subtracted y and then we multiplied by 1 over x plus 1 times x minus 2.
Mm-hmm.
And then we multiplied by 1 over y.
Yep.
Okay, so in the end, I think I end up with 1 over y prime is negative 1 over x plus 1 times x minus 2. Right? Do algebra. Everybody good with that? Okay, and then I think our next step is usually to take y prime and rewrite it as dy and put the dx on the other side. And then we slap a squiggle on this whole thing. Let's see. So I think all told there, I got to multiply by dx and then multiply by squiggles. Okay. So I got to here. Pretty sure that integrating, I'm going to get the natural log of the absolute value of y is, and then I have to integrate this friggin' thing. You guys all see the challenge there? Is this maybe recalling a challenge that's challenging?
Is this gonna be a PFD problem?
It is, yeah. So the first thing I want to do is kind of off in the margin, right? I'm going to perform partial fraction decomposition. And what I really need to do is I need to rewrite negative 1 over x plus 1 times x minus 2 in terms of some number over x plus 1 and some number over x minus 2.
To simplify things, you could just move the minus sign in front of the squiggle, but just so you don't have to deal with the minus sign in there.
Okay, sure. All right, and then you go find yourself a common bottom for this whole thing, right? So finding a common bottom, you get 1 is a times x minus 2 plus b times x plus 1. Everybody good with this? Okay, now this is the point at which you can apply a trick that you should not add to your brain as a math thing, but you should set it in the same place that you set that multiply by a squiggle bullshit, because it works, but I don't want you to think this. Does that make sense? Everybody with me on that? No? Okay.
I have no idea what you just said.
Suspicious, but continue.
I want you to know that this trick exists because I want you to use it because it's fast. But I don't want you to mistake it for being math because it's not.
Okay.
Does that make sense?
Yeah, I thought you already had explained the thing you were going to explain to us. So I was like, what did you say? So never mind.
Plug in x is 2 and x is minus 1. Why is this not valid?
So you're picking two different values for x in the same equation.
Good. And I'm also putting in the things that are going to make these 0.
Which
yeah.
means it's over
it's
0.
Over 0.
Or 0, or a over 0 and b over 0.
Yeah.
Yeah, I really shouldn't be putting things that are going to make the bottom of this 0. Because, well, because frankly, you shouldn't divide by 0. Like, this is not the point of the class where I tell you that now you can divide by 0. This is just the point of the class where I tell you there's a bullshit trick that looks a lot like dividing by 0 that happens to work most of the time for reasons. Okay, so if you plug these in, you're going to get, well, if I plug in x is 2, I'm going to get 1 is b times 3 guys with me on that? That means b is a third.
Oh, wow, yeah.
If I plug in x is -1, then the b term zeroes out, and I get 1 is a times -3. That tells me a is negative a third.
Hmm.
You guys with me on this? Okay. Seems like bullshit. Is bullshit. You can also check it. It actually works. This is a thing called Heaviside's method. We'll do enough partial fraction decomposition in this class that I want you to know that this exists, because otherwise it gets real tedious. That said,
I think the 4 or 5 PFDs that you have to do in this section already makes it tedious.
yeah, exactly. Like, we're going to have to do this a lot, so I'm going to give you this trick, even though there's not a great, like, there is mathematical validity here, but we can't see it with the tools we have. Does that kind of make sense? All right. So then I believe I have partial fraction decomposed this into seeing that I have a -1/3 times the integral of -1 over x plus 1 plus 1 over x minus 2 dx. You guys all on board with that? I plugged the a and the b back up here, and then I factored the 1/3 out through the integral. You guys all on board with that process? Okay, so this was basically PFD step. Okay, now my next thing is that I have to integrate those things. How do you integrate those?
Carefully.
Good man. Carefully. With some u substitution, maybe? Let u be x plus... Wow, you probably can't read that at all. Brownish. Let u be x plus 1 in the first one. Let u be x minus 2 in the second one. What's du in both cases?
dx.
dx.
Yeah, dx. Okay, great. This doesn't really change much. I'm assuming you guys are all pretty versed in calculus at this point. So I have -1/3, and then I have the natural log of the absolute value of x plus 1. Plus that one minus this one. Okay, what else did I lose?
Plus c.
Good, I lost a constant, so I need a constant. Everything agreeing with your steps so far, Jacob?
Yep.
Okay. All right, now my next step is going to be to solve for y. So I'm going to do e to the stuff to both sides. So I'm going to get an absolute value of y is e to the 1/3 log of absolute value of x plus 1 times e to the -1/3 log of the absolute value of x minus 2 times e to the c. So I did an e to the stuff and an exponent rule. On board? Okay. All right, now I'm going to rewrite e to the c as a, and then I'm going to do a plus minus to both sides. And I'm also going to grab these guys and drag them up into the exponents up there. Pretty good with that? Okay, so I'm going to end up with a y is a. Now, a here was positive. Here, a is simply not 0. Pretty good with that constant step. Okay, and then I have a absolute value of x plus 1 to the 1/3 power times an absolute value of x minus 2 to the minus 1/3 power. Okay, now what?
Plug in your x and y that they gave you initially.
Yeah, they gave me some x's and y's initially. If I scroll way back up here, I found out that, okay, so one, I should check whether a is 0 works. So does y is the 0 function? Does that satisfy this thing? The 0, let's see. So if y was the 0 function, then y prime is the 0 function. So is this crap times the 0 function plus the 0 function equal to 0? Yeah. Okay. So really I could scrap this. You could say, well, a is 0 works. Okay, that was one thing. Right, so really a can be anything. And then I need to take my initial condition. Right, so let me grab that guy. Drop that down here. Say, okay, so in the case that y of 1 is -3, then I have -3 is, let's see, well, I need to put in 1, right? You guys all see that? So I'm going to have a, and I've got 2 to the 1/3 power. I guess the absolute value of 2 is 2, right? Times the absolute value of -1 to the -1/3 power. You guys with me on that? Okay, so out of that, I get what? There's lots of negatives in that thing.
Is it 3 or -3 over 2 to the 1/3?
Yeah, so this whole piece is 1.
Yeah.
Right, because that's the absolute value of -1 is 1, which is why you needed to keep those absolute value bars, right?
Yeah, I think that may have been.
And then 1 to a power is 1. So I think I have -3 over 2 to the 1/3 power is a. You guys with me on that? Okay, so that means plug in. I got y is -3 times the absolute value of x plus 1 to the 1/3 over 2 times the absolute value of x minus 2 to the 1/3. Okay, and it looks like we could probably do a little bit of fiddling with this, but I'm not going to because I'm lazy.
You might want to put the 2 in the bottom x in parentheses, just so, because the top, it looks like you're multiplying 2 times x minus 2 to the 1/3 and not 2 to the 1/3 times x minus 2 to the 1/3.
Oh, you're right. I just forgot to put my... Thank you. Okay, so here now we get to the heart of Jacob's question, which is, I was supposed to... hide that. Pretend this doesn't exist. Sorry. My next thing I'm supposed to do is find the interval of validity, right? So if I go back and read the question... if I go back and read the directions, which I personally am bad about copy and pasting in here. So if I read the directions, they say, solve the initial value problem. this thing here is the solution to the initial value problem. Are you on board with that? What is this? Yeah, solid.
Figure out if there are any points where it isn't valid.
Yeah, we just want to know whether it's valid or not, right? Okay, so what would make this equation not valid? What makes this function problematic?
If x equals 2, then you get to divide by 0.
Okay, yeah, and in spite of my earlier trick, you're still not allowed to divide by 0, right? So I have a problem when x is 2. We all agree with that? Okay, so that seems like I should probably be saying something like, it's valid when x is not 2. You guys with me on that?
Mm-hmm.
Right? That's like looking at the real line and saying 2's bad. So, oh, but wait, hang on. Where did I calibrate this thing? What was my initial condition that I plugged in?
Y of 1 is -3.
So 1 lives on this side, right? So here's the trick with intervals of validity.
Oh, can it only be between the two?
The A can switch on the other side of a discontinuity to something else. Because Y of 1 is only left of 2. Right? So when you set this constant, you did it left of 2. And so you're not going to be able to get over 2 because there's a discontinuity in the way. You guys see that? Okay, so if we think about, this is the point where I calibrated my model, right? And so if I think about, okay, if I go a little bit over here, the derivative and everything's all good, right? So I think I can keep moving in this direction and be valid. Is there anything I'm going to run into that's going to stop my validity going left? Not really. I mean, the function's defined, the derivative's defined. Like, I think I'm good to go. So anything this way, I'm good with. Now, if I start heading to the right, we're going to have some points where we're valid. And then we're going to run into this thing at 2. And on the other side of 2, my constant's not calibrated right. You guys see that? No. Okay. Okay, let me phrase this with a kind of a simpler example. I think the heart of this thing amounts to having a function like y is a over x, right?
Mm-hmm.
Okay, now this initial value problem, right? If I tell you, all right, so y of 1 is 1. You guys with me on this? This would tell you, okay, so at time 1, right? Or at population 1, or at whatever our independent variable is, y is 1, or the response, right? So in the kind of easiest case, I'm thinking about a population. Right, so at y is 1, at time 1, population is 1. Now, if I ask, okay, so what about when y is -1? This thing doesn't tell you anything about that because this is only defined for times bigger than 0, because this solution stops working at 0. that make any sense? Okay, so our discontinuities are going to give us the edges of all the possible intervals. And then our initial condition tells us which interval we're in. And then the interval of validity is the interval containing that initial value.
I don't understand why you have to stop at that discontinuity, because the function still continues like after the discontinuity.
Sure, the function continues after the discontinuity, but you don't know about the values over there because you calibrated it for positive time, right? Like we calibrated this thing at time equals 1. And so we found the constant from the perspective of time equals 1. The perspective of time equals 1 doesn't tell us about the when time is 3.
So, for example, maybe at the discontinuous point, we're spending like 500 hours there instead of just one time or something. And like, it's once we're past that discontinuity, it's kind of all jacked up because we don't know how much time we spent at that discontinuous point.
Kinda. Yeah, it's really that the constant could be different on the other side. So if you think about this in terms of like some of the application problems we're going to be doing, those discontinuities happen when things like the tank overflows or the spring breaks or the mass goes to 0. So what do I know about the other side of the mass goes to 0 or the tank overflows or the spring breaks? Like, I just don't know anything about what that place looks like. Does that make any sense, Jacob?
I don't know. I'm still trying to fit it in my head.
Okay, so let me...
I guess, because when you solve for the initial value, you get a function.
Mhm.
That function shouldn't change past the discontinuity.
Oh, it's just that we don't know what happens to it. Right? When I plug in, when I say, all right, so this population makes sense for positive time. Right? When I plug in t equals 1 and then calibrate the model, right? That's me solving for that initial constant. So that's me saying, all right, when time is 1, the population is 200. And then going forward, it works this way. Well, if the model that I've got has a discontinuity at 0, then the question, what does this population do for negative time, doesn't even make sense because you can't get there from here. Is this making any sense at all?
I think saying that with Jordan's sort of analogy works.
Okay.
But it only works on like a conceptual standpoint for me, not really on a mathematical standpoint.
Oh, I see. Sure. So does this solve? Let's ask, does this solve, right? So is this function with my constant in it, is that a solution to the initial value problem?
Yeah.
Absolutely yes. When does that stop making sense?
At the discontinuity.
Yeah, it stops making sense at the discontinuity. So if from time 1 to time 2, I'm all good, and then at time 2, the tank overflows or the mass disappears or the spring breaks, what can you tell me about time equals 3?
I suppose.
You just can't tell me anything. If we had calibrated this thing for time equals 3, then you could tell me stuff about time equals 3, but you can't tell me stuff about time equals 1.
Okay.
Because you can't flow time backwards over 2.
So if I were to say, take that equation, solve for a point on the right of 2 for like 3 or something, and then plug that number into our initial equation that wasn't solved for initial value, and then solved for y at 3 or whatever, would then that interval be, or would we then have an interval past 2?
So if we took our initial conditions, right?
Yeah.
And you said, okay, so if my initial conditions were y of 3, then I would get a solution that was valid from 2 to positive infinity.
Yeah.
If I try to stitch those together, it's fine. Like, it's not going to break anything mathematically, but it doesn't make any sense model-wise.
Okay.
Like, we have to remember that these things are attached to models of reality. And what a discontinuity means in a model of reality is that something broke. And so to go from we're all fine and then something breaks and then something else happens. I mean, could you construct a case where that makes sense? Yeah, for sure. Would the math still work out? Yeah, for sure.
Okay.
You guys see that?
That makes more sense.
Yeah, if you think about the interval of validity as being, when does this model work for this initial condition? This is really amounting to when can I expect my predictions to hold?
Like if
That
you
sort of
have
follow?
like an exponential decay or something.
Yeah, if I have exponential decay, then I can expect my prediction to hold for all of infinite time forward and backwards.
Well, except for less than 0, where there's a discontinuity.
In exponential,
Decay?
so if I have exponential decay, right?
Oh, no.
The model I'm
you
saying
won.
is
Never mind.
y is a e to the minus kt.
Never mind.
Yeah, and the cool thing about this one is it doesn't have discontinuity. So my my interval of validity for this one is from minus infinity to infinity. You guys see that? Sometimes that interval of validity will be given by the function that you're getting here. Sometimes it'll be given by the physical reality of the situation. Like, you have a 500-gallon tank, right? If it's filling up at a rate of a gallon a minute, at time 500, you're going to run into problems. I don't know what happens at time 500. If the tank's sealed, well, then it probably pops. Or the outflow rate has to increase or something. Like, something's going to happen there to qualitatively change the situation.
But mathematically, the function has no way of knowing that.
Yeah, so depending on how I build it. So in one of our further chapters here, we're going to get into some like nitty-gritty of building discontinuous functions for stuff like that. And that's going to be one of the more powerful things we learn in the subject, is how to deal with that. Like, we're going to build that into the model, and then we're going to be able to solve models with those things built into it. For right now, the only ones I'm going to see are in the math, and frankly, because they're not attached to a physical model, those discontinuities aren't maybe going to make the greatest amount of sense. Does that sort of follow? Okay. Let's see. What else did I have on my question list?